Welcome to this real analysis lecture. In this video, we will study bounded and unbounded sets. We will also learn two very important concepts called the supremum, also known as the least upper bound, and the infimum, also known as the greatest lower bound. These concepts form the foundation for many advanced topics in real analysis. Let us begin with the idea of a set that is bounded above. Let us first understand what it means for a set to be bounded above. A set S is said to be bounded above if there exists a real number m such that every element of the set is less than or equal to m. Mathematically, we write this as for every x belongs to S, x is less than or equal to m. Such a number m is called an upper bound of the set. An important observation is that a set does not have just one upper bound. If a set has one upper bound, then it automatically has infinitely many upper bounds. Why? Because any number greater than m will also be greater than or equal to every element of the set, and hence it will also serve as an upper bound. This naturally leads to the interesting question: among all these upper bounds, can we find the smallest one? That question will lead us to the concept of supremum. Now let us discuss the opposite concept, that is bounded below. A set S is said to be bounded below if there exists a real number m such that every element of the set is greater than or equal to m. Mathematically, we write this as for every x belong to S, x is greater than or equal to m. The number m is called the lower bound of the set. Just as a set can have many upper bounds, it can also have many lower bounds. If a set has one lower bound, then it automatically has infinitely many lower bounds. This is because any number smaller than m will also be less than or equal to every element of the set, and hence will remain a lower bound. Later, we shall see that among all lower bounds, one particular lower bound plays a special role. It is called the infimum or greatest lower bound. Let us now compare bounded and unbounded sets. A set is called bounded if it is bounded both above and below. That means there exist two real numbers, small m and capital M, such that every element of the set lies between them. In other words, m is a lower bound and capital M is an upper bound. A set is called unbounded if this condition fails. There are different ways in which a set can be unbounded. A set may not be bounded above. For example, the set of natural numbers keeps increasing without limit, so it has no upper bound. A set may not be bounded below. For example, the set of negative integers extends indefinitely in the negative direction. Finally, a set may be neither bounded above nor bounded below. The set of all integers is a good example because it extends indefinitely in both directions. Understanding whether a set is bounded or unbounded is the first step toward studying supremum and infimum. We now come to one of the most important ideas in real analysis, the supremum. Suppose a set has many upper bounds. Among all these upper bounds, if there is a smallest one, then that smallest upper bound is called the supremum or least upper bound. We denote it by M equals supremum of S. To verify that M is the supremum, two conditions must be satisfied. First, M must be an upper bound on the set. Every element of S must be less than or equal to M. Second, no number smaller than M should be an upper bound. In simple words, M is the tightest possible ceiling for the set. It is an upper bound, but moving even slightly below it destroys the upper bound property. This idea is fundamental to the completeness of the real number system. This theorem gives a very useful characterization of the supremum. A real number M is the supremum of the set S if and only if two conditions are satisfied. The first condition is familiar, that is, M must be an upper bound of the set. The second condition says that for every positive epsilon, no matter how small, there exists an element X in the set such that X is greater than M minus epsilon. What does this mean? It means that M minus epsilon cannot be an upper bound. There is always some element of the set that lies beyond it. In other words, elements of the set can get arbitrarily close to M from below. This perfectly captures the idea that M is the smallest possible upper bound. Any attempt to move below M, even by a tiny amount epsilon, will fail. This epsilon characterization is used extensively in advanced proofs throughout the real analysis. Just as we have the least upper bound, we also have the greatest lower bound. If the collection of all lower bounds of a set has a greatest member, then that member is called the infimum or the greatest lower bound. We denote it by small m equals infimum of S. To establish that M is the infimum, two conditions must hold. First, M must be a lower bound. Every element of the set must be greater than or equal to M. Second, no number greater than M should remain a lower bound. In simple terms, M is the tightest possible floor of the set. It is a lower bound, but if we move even slightly above it, the lower bound property is lost. The concept of infimum is completely analogous to the concept of supremum. This theorem provides an important characterization of the infimum. A real number M is the infimum of a set S if and only if two conditions are satisfied. First, M must be lower bound of the set. Second, for every positive epsilon, there exists an element X in the set such that X is less than M plus epsilon. This means that M plus epsilon cannot be a lower bound. There will always be an element of the set lying below it. In other words, elements of the set can come arbitrarily close to M from above. This shows that M is the greatest among all lower bounds. Any attempt to move above M, even by a very small amount, fails. Let us now discuss some important observations. The supremum and infimum of a set may or may not belong to the set itself. Consider the closed interval from A to B. Since both endpoints are included, A and B belong to the set. Next, now consider the open interval from A to B. Here, the endpoints are excluded, so neither A nor B belongs to the set. Another important fact is uniqueness. If the supremum exists, then there can be only one such number. Similarly, if an infimum exists, it is also unique. A set cannot have two different least upper bounds or two different greatest lower bounds. Let us now connect supremum and infimum with the familiar ideas of maximum and minimum. If the supremum itself belongs to the set, then it becomes the greatest member of the set, also called the maximum. Similarly, if the infimum belongs to the set, then it becomes the smallest member of the set, also called the minimum. An important consequence is that every finite set contains both its supremum and its infimum. Therefore, every finite set has both maximum and minimum element. We now arrive at one of the most fundamental properties of the real number system. The order completeness axiom states that every non-empty set of real numbers that is bounded above and possesses a supremum in the real numbers. As a consequence, every non-empty set that is bounded below possesses an infimum in the real numbers. This property is known as order completeness. It tells us that the real number line has no gaps. Whenever a bounded set seeks a least upper bound or greatest lower bound, the required number exists within the real numbers. This is not true for the rational numbers. There are bounded sets of rational numbers whose supremum is not rational. Thus, the completeness is one of the most important features that distinguishes the real numbers from rational numbers. Now let us conclude with some examples. Consider the set consisting of 1 of 1/3 and so on. The largest element is 1, so the supremum is 1. The terms get closer and closer to 0 but never reach it. Therefore, the infimum is 0, which does not belong to the set. Next, consider the set of natural numbers. The smallest element is 1, so the infimum is 1. However, the set grows without bound and therefore it has no supremum. Finally, consider the empty set. Since the empty set contains no elements, every real number vacuously satisfies the conditions of being an upper bound and lower bound. As a result, there is no least upper bound and no greatest lower bound within the real numbers. These examples summarize the key ideas of boundedness, supremum, and infimum that form the foundation of real analysis. Thank you for watching and see you in the next lecture.